Well, thank you very much, and hello to my friends in Aachen and elsewhere on the way to Bangkok. And you'll forgive me if things are a little disorganized here because it's 11 p.m. and I have actually been asleep for a little while, and so I'm still a little sleep fogged. I want to talk to you about some, what I hope you will find is rather exciting joint work with Frances Kuo, Vesa Kaarnioja, Fabio, Nobile, and Yoshihito Kazashi over recent years on kernel-based approximation methods, which we have found surprisingly powerful, and I hope you will think interesting as well. So I'm going to talk about parametric PDE with a large number of parameters. And I particularly mention a recent paper with Vesa and Frances on kernel approximation and serendipitous weights. So you have to wait to find out what they are. So, excuse me while I just try and fix up my own screen because it's a bit blocked by this, by a banner at the top. Anyhow, there we are. So let's take this example of a familiar kind of example of a parametric PDE, elliptic PDE, with a solution U tilde of x the physical variable on a domain D and 1, 2, or 3 in 2 or 3 dimensions, and also depending on a parametric vector z, if you prefer. I'll try z, z, which is a vector with s components, and so it represents our parameters. So at the permeability, the coefficient here, a tilde x of z, is of the form a bar, which is the mean, plus the sum from 1 up to s of zj, the j component of z, times psi j of x, where this is a given vector, and the z1 up to zs are parameters representing independent random variables distributed on -1 to 1 with some probability density function. Excuse me again, I'm just having trouble with my own screen here. So examples, the most common, I suppose, is the uniform case in which rho of z, the density of the variable zj, is 1/2. Obviously, the uniform case. And on the other hand, I'm particularly interested in rho z is 1 on pi, 1 on z squared to the -1/2, which you will associate in a natural way with Chebyshev polynomials of the first kind. Now, there are, as you will all know, many methods for tackling such problems: polynomial chaos, generalized polynomial chaos, stochastic Alerkin, stochastic collocation, to approximate the z dependence. Most of these methods, because you've got both z and x, the physical variable, z the stochastic variable. Most of these methods use the basis of multivariate orthogonal polynomials. And in the particular case in which rho z is 1 on pi, 1 on z squared to the -1/2, GPC, generalized polynomial chaos, uses products of Chebyshev polynomials of the first kind. So j equals 1 up to s and Lj up to some degree. So there's a problem when S is large with this way of doing things, because, I mean, as you probably well know, I mean, the basis set that one is dealing with grows very fast, exponentially fast with dimension. So I've just written down here how it is with the S dimension. You've got S variables, Z1 up to ZS. Your basis functions are products of T up to L1, Z1 up to T, LZ, ZS, multiplied together for each function L from 0 up to M. I think I've been inconsistent here. Contains L plus 1 to the S or M plus 1 to the S basis functions. So I mean that grows enormously fast. Even if you take polynomials only up to degree 1, you have 2 for each dimension and 2 to the S basis functions in total. So you face always, everyone who writes about this talks about the curse of dimensionality. and hence the need to make a clever use of sparsity to leave most terms out, most of the basis functions out, since otherwise you are dead by the curse of dimensionality. So for the special case of the density rho z is 1 on pi times root 1 minus z squared, life is much easier if we change to a periodic model of stochastic variables, as we introduced in an earlier paper with Frances and Vesa Kaarnioja. So I want first to talk about this change of variables because it is sort of rather crucial to the way that we work. So what we do is to change the variable z, each variable z, zj, to a new variable yj through the transformation zj is sine 2 pi yj on the second line there. Zj is sine 2 pi yj with yj running from 0 to 1. And so our permeability function or a diffusivity is now instead of a tilde xz is now axy, and each component of y comes from zj is sine 2 pi yj. And so it now looks a little different because now we have a bar plus sum of sine 2 pi yj psi j, and the y's, each component yj is now independent, identically, uniformly distributed on 0, 1. And this works because, well, you have a little theorem here which we proved that if z is a random variable distributed on -1 to 1 with density as stated, this Chebyshev of the first kind of density, and y is a random variable uniformly distributed on 0, 1, then the probability that z is less than or equal to t, or any t, real number t, is the same as the probability of sine 2 pi y is less than or equal to t. The probability distribution is the same. We have not changed the model at all. And so I've written an indicator, the proof. And so the proof, what in the proof, you look at the probability that z is less than or equal to t, the integral of the indicator function times the probability density. We change to a new variable y. We put z is 2 sine 2 pi y. And the only problem is that sine 2 pi y is not monotone on the interval 0, 1. It is not monotone. But on the other hand, what we easily see, it is monotone on the smaller interval -1/4 to 1/4. And so it is, we then make I'm sorry, it's monotone on the, yes, monotone on that interval. So we make a change of variable on that interval in a straightforward way, and that gives us the probability that z is less than or equal to t is to equal to an integral of this indicator function t minus sine 2 pi y dy, and similarly it's monotone on the interval from 1/4 to 3/4, same way, monotone the other way. I would like to show my, I'm not sure whether you can see my hands, but if we got two results there, the sign of the probability that z is less than or equal to t is equal to two integrals. You add them together, you get the integral from -1/4 to 3/4. That's the integral over a full period. The integrand's periodic. We can make it integral 0, 1, and that is the probability that y is less than or equal to sine 2 pi y is less than or equal to t. So anyhow, that's how it goes. So formally, we have not changed the model. We're using a model that is familiar, is one of the commonly talked about models in GPC, but the approximation that we're going to use is completely different. Instead of using polynomials, which leads us to the curse, we take a kernel-based approximation, an approximation that makes no use of sparsity and does not suffer from the curse dimensionality. I will show you numerical examples with remarkably high dimension in due course. So we're going to use a kernel approximation given a real valued function f. So for the moment, I talk just about a function defined just of the stochastic variables. Forget the physical variables for a moment. So the kernel approximation of f takes the form of a linear combination of kernels k anchored at tk. So it's a linear combination sum of ak k of tky. The capital K is a kernel, and I will be more specific, but kernel, it's got to be, so I will assume always a kernel, positive, definite, and I will be more specific. But with any kernel, a kernel interpolant based on these points is the linear combination of those anchored kernel at, I'm sorry, I didn't mention at the points. It's kernel interpolant based on prescribed points, T1 up to Tn in our integral, and now we fix the function, the coefficients ak by this condition. We have interpolation that our function fn tk is f at tk is a given function. So we are having an interpolatory approximation, and that then of course leads us to a linear system for the coefficients ak, in which the matrix k, tk, tk prime, well, it's a symmetric matrix, a symmetric positive definite matrix because it's a kernel. So the matrix typically dense, but on the other hand, very poorly conditioned, typically. And solving a linear system is actually a major problem when n is large in general, but not for us because of the way we're going to do things, in the particular way we're going to take our kernel. We take our kernel to be the reproducing kernel of a particular Hilbert space H, a reproducing kernel Hilbert space of periodic functions within which the function f is supposed to live. And we're going to be dealing now with periodic functions. Remember, we've changed our model so that the input parameter is now periodic, and the solution is therefore also periodic. And so reproducing kernel just says that there's the standard properties, but of which the third one is the crucial one, that the inner product in the Hilbert space H with the kernel just gives us back the function value at y for all f in H. And so I want to tell you what we will see as an important result. But so this is work, actually a result from just 2 weeks old now, less than 2 weeks old. That if H is H alpha depends on some smoothness parameter, so K we can write as K alpha, then this is a curious sort of theorem, I suppose. Suppose that we have an error bound which is of the form f minus our kernel approximate is in the L2 norm is less than or equal to some constant, some number times the norm of f, the H alpha norm of f, or some constant, some number C alpha n. And then suppose also that that we have this relation between the Hilbert space H alpha and the Hilbert space with twice the smoothness stated there. Then for a function which is smoother, it belongs to H2 alpha, the L2 norm of the function of the error of G, of the interpolational error, is less than or equal to constant, which is the square of the previous constant. And that means that we get, if you start with for all functions in f, if you have a convergence rate of n to the minus alpha, if the worst case error goes like n to the minus alpha, then for a smoother function in H2 alpha, the L2 error goes like n to the minus 2 alpha, double the rate of convergence. So this seems to be a new result and will turn out to be important for us later. And I thought it useful to just get it over here, and I will come back to it later. So what is the space that we work in, and therefore what's the kernel we're working in? So we choose something that's as useful and as simple as possible. We take an unanchored weighted Sobolev space of dominating mixed smoothness of order alpha an integer, alpha 1 one degree of smoothness. Expressed in terms of derivatives here, is the sum over all subsets of 1 up to s. S is the dimension, the number of stochastic variables. There's a constant in the we have in the denominator there we have a gamma u, which are weights. I will come to that later. But the integral of the square so we separate here the variables that are in U, which are yu denotes the components of y that belong to the U, and y minus u the others. We differentiate alpha times with respect to the variables yj that are in U, for j and u, and we integrate out the others. We integrate in the inner integral with respect to y minus u within square, and we and integrate over the variables in U. So that looks complicated. One can also express it in Fourier series term, which is how the work is done. But so here's the corresponding kernel. The beautiful thing about that particular choice of our function space is that the kernel uniquely determined by the inner product. That the kernel is very simple in a certain sense. You see, it is the sum k alpha y prime is the sum over all subsets of those weights gamma u, the red ones, times the product of the j in u for each subset u of given functions eta alpha, where the eta alpha are non-periodic functions of a single variable. And if you know your classical analysis, then you recognize that those particular Fourier sums are in fact related to Bernoulli polynomials. Apart from a coefficient, they are Bernoulli polynomials. So this means that Bernoulli polynomials in which the argument is the integer part of y. But this means that that's a very explicit, simple expression, isn't it? A simple expression, a Bernoulli polynomial degree 2, just to given this polynomial, this quadratic polynomial y squared minus y plus 1/6, 3 to the 4 is written there, and they're all known. You can go as high as you like, and everything is known. Because I show you what a kernel interpolant looks like, and it can be a little horrifying, but let's explain that the kernel interpolant of a constant function here. So here S is two dimensions. Alpha is 1. There's the Bernoulli polynomials. Well, come out of Bernoulli polynomials of degree 2. Because it'd be, just me just go back for a moment, be 2 alpha. Yes, eta alpha is in B2 alpha. So this is the B2, but Bernoulli polynomials of degree 2 have they are continuous, but they have a discontinuous first derivative. And so this is a kernel interpolant using just 5 points, and we'll come to what the points are in a moment. But it's a terrible approximation of the function 1, isn't it? Because it gets down to very small values. And just to look ahead, the problem here is, why is that so bad? And that's bad because those weights in there, remember there's a weight for each subset. So the weight for the empty set is 1. Now that sets our standard, that's defined. But the weight for all the other subsets of the subset of 1 alone, of 2 alone, 1 and 2 together, all equal to 1. That's the classical situation. The classical situation is that the weights are much too big. So if you have a smaller weight, you can get a good approximation in the uniform sense, but of course you always have discontinuities in the partial derivatives because of that, because that's the way the Bernoulli polynomials are. So a good choice of the points. Now to use lattice points, rank 1 lattice points, following an idea of Hickernell and colleagues, going back a long way, but I think not much used since that time. So the interpolation points here are now multiples of multiple k. Tk is k times a generating vector, integer vector z, integer vector, z gen divided by n, and we then take the fractional part. So these are lattice points for rank 1 lattice rule, and I suppose that most people in this group have probably seen such things, but as a simple example of a good lattice in 2 dimensions with 34 points, which is a particular Fibonacci number. Z gen is 121 and 21, 34 are consecutive Fibonacci numbers. That's a good construction in 2 dimensions. And so how does it go? Well, you'll see at the bottom, that's the formula. TK is, oh, I'm sorry, I didn't explain that the braces mean take the fractional part, or otherwise you'll fall outside the unit cube. But taking the fractional part, you'll see that, well, these are the success points, and they're a very nice sort of looking array, but it wasn't obvious from the vector z. So finding a good vector z is part of a long-standing story in the whole use of lattice rules for numerical integration. But okay, so what's so good about using lattices? Well, look, it really is good. The matrix elements become then just a function of the k minus k prime of z gen. Sorry, there's a mistake there. It should be z gen on n and 0. They just depend on the difference. Well, that was already apparent. But this means that, well, what it means, if you look at it carefully, that each row of the matrix is exactly the same, except shifted along by 1. Each row of the matrix is the same, but shifted along by 1. You increase by k, increase k by 1, and increase k prime by 1, and there you are. You have the same result. So the interpolation matrix is a circulant matrix, and that makes the linear algebra problem, which is a major concern of all interpolatory methods, making it so easy to invert and solve by fast Fourier transform. It needs only order n log n flops, and the fact that it's ill-conditioned in practice presents not the slightest problem at all, because when you use FFT, effectively you reduce it to a one-dimensional problem, and the condition is just not an issue. And okay, well, what about weights? Well, there are different kinds of weights. In principle, you can have one weight for each subset of the variables, but that's just impossibly difficult. But in this very important special case, if the weights are of the product form, which means for each subset U, gamma U is just a product of something of parameters of weights, we would say, for each variable J that is in the subset U. And it's easy enough then to see that the kernel is then just a product. It's no longer a sum of 2 to the S subsets. It's a product of S things. And is it clear how that goes? If you look at that product and just write out the factors, 1 plus gamma j times 1 plus gamma j, just write out the S factors, multiply it all out, you see that you get a sum over all the subsets of the variables. So that's exactly what we had for the kernel. But for product weights, this method is actually very fast for doing interpolation. That the method can compute the interpolant at m arbitrary points in a time of order, well, I've written it down there, the capital order. So the first term, Tn, is just the time to compute the interpolant. So capital T is the time for single function evaluation. To solve the linear system is of order n log n, and then to find the function at a particular point is S for the product, n for the number of lattice points, times m at m arbitrary points. So that's actually very fast, and linear in S and linear in n. Okay, so how to choose the generating vector? Well, as in lattice rule integration, we like to choose it to give a small worst case error. Worst case, in this case, L2 error in the Hilbert space H. So what's the worst case error? The worst case L2 error for some algorithm A, which from H into L2, is defined there at the E of A, L2, and H. It's the primum or maximum of the norm of F minus AF, L2, for all F in the unit ball of H, for all F in the H norm, norm is less than or equal to 1. So how we choose our Z gen is by component construction. The first component take to be 1, and then in turn you fix Z2, Z3, and so on, ZS in a greedy way by progressively minimizing the worst case error for that dimension or some related quantity for dimension Z2 up to S respectively, and keeping all earlier components fixed. So it's a well-developed technology as well, way out of what I wanted to talk about here, but that's how we do it. The worst case error depends on the weights. We have to fix the weights, which I will come back to. How to fix the weights? Well, I wrote the worst case error, so that from the definition of the worst case error, it follows if A is linear, that the L2 error for given function F is now, it's easy to see that it's now bounded by the worst case error times the norm of F. And that's the principle we like to use because it's very sort of definite. That we will now compute our error, we'll now control our error, and in principle we choose our weights to control that product of worst case error times the norm. And that means, by the way, just to continue on that theme for a moment, that means that you see it depends not only on the worst case error, which is an abstract sort of thing you might say, but it depends also on the norm of F for the particular function F. So that means when you're working this out, with working with this bound, you need to know what is the norm of F, a hand-up estimate for it. In fact, we work with upper bounds for both factors in there. The kernel interpolant then is by A star is known to be, this kernel interpolant with reproducing kernel Hilbert spaces is optimal in the sense of minimizing the worst case error. That's a well-known classical property, and because of that, that means our error bound with A star is now our kernel interpolant. A star of F is our kernel interpolant, is bounded by the worst case error for any other algorithm that uses the same points. Any algorithm A that uses the same points, that uses information at the same points, times the norm, and that's how we proceed. Well, for upper bound, in that comparison, we use a trigonometric rule, and it gives us a known result from a paper by Kuo and Kuo, Nuance, and Sloan in 2020. It gives us a specific upper bound on the worst case error. So there we are. That's for n primed. I've written it in a recent paper by when Mo. And from coming out of Belgium, the result can be extended to composite n, and so available for all n. Now the proof is constructive, so that means that the component by component CBC algorithm not only shows that there exists such a there exists such that excuse me. But also gives you the construction. It's proved by construction at each step. Okay, so if we just look at that result that we have, but I didn't concentrate on the fact that lambda is not fixed. Unfortunately, this is a little bit complicated. This upper bound on the worst case error, which is the part in black, because it's for all lambda that are bigger than 1 on 2 alpha, and you would like to take lambda equal 1 on 2 alpha, but if you do that, then you see that that's a zeta function in there, and the zeta function is 2 zeta alpha lambda, the zeta function blows up for argument equals 1. So you cannot take lambda as small as 1 on 2 alpha, but we take it to be close to 1 on 2 alpha, and then the rate is n to the minus alpha on 2 plus delta. That's interesting that it's n to the minus alpha on 2 plus delta. In fact, that's the best possible convergence rate for L2 approximation that uses lattice points. It's a remarkable fact. I think it's a very clever argument by Byron Hyde, Kammerer, Ulrich, and Volkmar in 2017 that you cannot do better than n to the minus alpha on 2, given if you use lattice points. Whereas it's suboptimal if you're allowed to choose any points, given that the optimal rate of convergence for L2 approximation in H is n to the minus alpha. Okay, so that's something we live with, that we have a suboptimal rate for our worst case error. So now I'm getting on to the parametric PDE case. I want to sort of show you how we've done. We've got the machinery available now. Now I take a specific problem, which is given in full in this paper with Fabio and Yoshihito in Numerical Mathematik in 2022. And so it's just a general problem that I wrote down before. It's two-dimensional. It has a particular right-hand side, x2. It doesn't matter. It's two-dimensional. The domain is the square, unit square, and our coefficient, diffusion coefficient is 1. The mean value is 1 plus sigma j sine 2 pi y j psi j with particular psi j. And I just dwell on the psi j a little because it's how you choose the psi j, and our psi j, well, it's a constant times sine 2 pi x1 sine 2 times j 2 pi x2. But what I really want to focus on are those numbers out the front, c and j times minus theta. Those are the two variables that control how difficult the problem is. You see, by taking c bigger, and by taking c bigger, you make the diffusion coefficient much bigger. You make it much bigger. If you take it too big, you will destroy the ellipticity of the problem. So there's a limit on how big you can take it. The theta controls the rate of decay of these terms. It therefore just controls the real dimensionality of the problem. If theta is close to 1, because we need it to be bigger than 1 to make sure that to give us uniform convergence, absolute convergence. If theta is close to 1, then you have a lot of terms in the sum, and you have high dimensionality, high, real, true, effective dimensionality. And we try it with large values of S. So I'll show you how it goes. Well, I admit I've got to just comment. We haven't finished yet. We still have to estimate the H norm of our parametric PDE. And it's sort of known how you do this. You differentiate the PDE and keep going, and we work on that. We make a choice of weights that makes an upper bound. We would like to minimize that product of the worst case error times the norm, but we make it small anyhow. With this choice of gamma u, we compute by component the integer vector that does the lattice points. So you sort of use lattice points, and we use an error bound, which is the L2 error bound with respect to both the physical and the stochastic variable. Square root of the integral over d and the integral over 0, 1 of the s, all that, and we get that it's of order n to the minus, alpha on 2 plus delta times explicit constant, which the way we've done it now it turns out to be, this is a lot of analysis, a lot of detail here, but independent of s. It doesn't matter how big your cutoff is, it is independent of s, so it is bounded by something, which with the infinite case you could say. So there's our error bound, and I've still left it there in terms of the gamma u. It's of course a little bit complicated, but the top line of the error bound, there's L2 with respect to both physical and stochastic variables, So it's the worst case error on the top line and the estimate of the norm in the second line. Both factors depend on gamma u, and that's why you need to balance them. You need to choose gamma u that is neither too big nor too small, because if it's too big, the first factor is too big, and if it's too small, the second factor is too big. So that's the compromise that you have to make, and we know how to do that. And so the first thing we thought to do was to make it as small as possible, as I said, and in the paper of our 5-author paper, we found a good choice for which we can prove things. So there it is. There it is. It's a little complicated, but and I don't want you to dwell on the details, but for these weights, as I said, the error bound, L2 error bound, bounded by a constant times n to the minus alpha on 2 plus delta for arbitrary delta. The C delta is known explicitly, remember, in terms of zeta function and all that sort of thing. It's known explicitly. It depends on delta, but is independent of S, of the dimension. So what happens? You take delta, you try and get a rate close to alpha on 2, and the constant blows up. All right. So how does it go? Well, it works. It depends on how hard the problem is, of course. So what I've done in these pictures, and I would just like to spend a moment explaining the pictures. So here we're looking at two graphs. So it's S equals 10 on the left and S equals 100 dimensions on the right. What we're looking at is so the parameters are, I consider this sort of a middling case. Theta is 2.4, it's bigger than 1. We get convergence like j to the minus 2.4. A small constant, small c, and alpha is 4. Alpha is 4. 4 is a smoothness. And so it works pretty well. I mean, so the red dots are, we're looking at the number of nodes as the horizontal axis, 10 squared, and 10 cubed, and so on, going up to 10 to the 5th. And the error on the left-hand side going down to, well, for S equals 10, going down to 10 to the minus 11 or so, and in a steady way. And similarly, with similar results, even for S equals 100. So by the way, probably just means that you don't really need 100. S is the effective dimension is not much more, it's probably less than 10 here. We don't know what's the effective dimension because we don't leave anything out. We just leave everything in and just compute, just go ahead. But I wanted to explain that dashed line up there. That's our theoretical prediction. It's that n to the minus alpha on 2, or actually even worse than that, because this is based on the actual kernel that we use. So we wanted to get a result independent of dimension. So that is the rate. But when the graphs were drawn, we didn't know this result that I quoted earlier, the double rate of convergence. The double rate of convergence. So actually that gives a slope, but it should be doubled to give our theoretical rate. So we certainly actually do better. We don't do as well as we don't see the new rate, the double rate of convergence. So this now is looking again with S equals 10 on the left and S equals 100, but this is a harder problem. So you see theta is now 1.2, which is marginal. Theta, remember, you need theta bigger than 1, or you don't get absolute convergence of the sum for the diffusion coefficient. But it's still working beautifully for S equals 10. Your error is going down to 10 to the minus 8, and ridiculously small, and even for 100, it works well. So now we like to push things to their limits. So this one is again S equals 10 and S equals 100 on the right. But now we see that, and this is for harder set of parameters, and theta is 1.2, that's the same as the last one, but C is now 0.4, which is twice as big. And you can see that this is a very difficult example, because if you can see the legend at the top of the graphs, it shows you the minimum estimates of the minimum and maximum values of the field if the parameters take their extreme values. And the minimum, you see, so the field ranges from about 0.1 up to 2. The mean is 1, remember? But if that diffusivity coefficient ranges in values all the way from 0.1 up to 2, so you're nearly losing ellipticity. If it gets to 0, you're in trouble. So it's a harder problem, and you can see what happens. Those red dots for s equals 10. Yes, if we're prepared to take 10 to the third, 10 to the fourth points, yes, we are getting there. We're into asymptotic region or something. We fail completely for s equals 100, and we publish this result because we think it's important to know when things don't work as well as when they do work. But anyhow, this is not the end of today's story, because well, the predicted, well, I said the convergence rates are out of date and need to be doubled. Yes, that's true. But more than that, the weights that we used there were not product weights. So I told you before how good, efficient product weights are, but they are not product weights. They're not. These are called spot weights: smoothness, driven product, and order dependent weights. But they're not products. They're complicated and not products. That means they can be implemented, but because of clever design work by the Belgian group, especially with Frances, but the kernel is now expensive to compute. Remember, the kernel depends on the weights. These weights really matter to us. Let me just think about weights for a moment. To us, the weights really matter because they appear twice in our actual implementation. They appear first in determining the generating vector, right, in our CBC constructing of the generating vector, but they also appear in the kernel explicitly. The kernel, in terms of Bernoulli polynomials and so on. How you implement this is not obvious, but it can be done. But that's why the cost is of order s squared nm, with not a good constant either, and the offline cost for computing the generating vector is of order s cubed times n, whereas for product weights we don't have anything like that. And so can we do well? We asked ourselves, can we do well with just product weights? And the answer is yes, we can do well with just product weights, and we discovered by accident there are what we call serendipitous weights. Serendipitous weights are product weights, and what we did to get them is to omit the part that makes, look, the spot weights are much too large. Do you remember what we saw what happens with an interpolating polynomial if the weights are too large? The interpolant is 0 over too much of its range, except at the interpolation points. And that's why we get such bad results in the end, in that hardest problem. So Frances's idea is that we just leave out the problematic factorials coming from the estimation of the norm that make the weights too big. So we just left them out and obtained serendipitous weights, so-called. Now, I wanted to emphasize we still have an error bound, right? We have an error bound for all weights, error bound for all weights. The rate of convergence is the same for all weights. It's just the constant that makes the difference. And so we tried this. It's very easy to implement. They're quite explicit, very easy to implement. And now I show you numerical results again. And so this is now the triangles. I'm sorry, the legions is slightly different, but the red are the same as before. They're the spot weights. And what we find in this easier case, well, for C is 0.2, it's not so easy because the theta is 1.2, but we do about as well. So I want to tell you the lesson that we found is that for easy problems, we do about as well with our serendipitous weights as we do with spot weights. Whereas for harder problems, we do spectacularly better. So this is the hardest problem. For the case, yes, theta is 1.2. It's very marginal. It's close to breaking the boundary of ellipticity, and C is 0.4. That was the hardest problem, and the red diamonds there show you how it was before. Remember, we failed completely. On the left, we got S equals 10. On the right, we've got S equals 100. And we failed completely with the spot weight for S equals 100 for this hardest problem. But the serendipitous weights are doing phenomenally well. And we found that this is absolutely consistently so. And it led me, I mean, so in some sense, what we're finding is that this is not a hard problem. So I asked Vesa, who was doing the calculation, I said, look, why don't we try something, just show we can just go a bit further. Why don't you try, let's be outrageous and take dimension 400, S equals 400 dimensional problem. So he went away and came back a week or two later with results for S equals 1,000 serendipitous weights, and we're using serendipitous weights, and we can still do. So we have nothing to compare with now, except what we're comparing with our own calculations, of course, with even more points in our approximation. But so we are clearly doing. We're extremely able to cope with this, and it's clear that even for S equals 1,000, we do not, in fact, need as many. Well, let's say if we use 10 to the 4th points, we get 10 to the -3 error. With a 1,000-dimensional problem. I don't think I've ever seen anybody do a calculation like this, and I think it's an interesting challenge to people who, believe in who want to use other methods to try it on a hard problem like this. So I'm coming to the end. I've rocketed through. So we're now looking at high-dimensional approximation in a, we think, quite realistic application. But this is the diffusion problem. This is the elliptic problem, which is certainly much easier than anything. We don't claim we can do hyperbolic problems at this time. The approximation can be both mathematically rigorous and feasible for large dimensionality and large numbers of points. The cost is merely linear in S, and I should have said linear in S and linear in N if we use our periodic random variables and serendipitous weights. We're not doing anything completely different from what's been done before, because this is the probability model. It's the same as for the underlying problem. It's the same as for GPC with Chebyshev of the first kind as our weight function. So this is actually the recent book by Badcock and others. This is one of the two probability distributions that's talked about in the book. One is the uniform, and this is the other one. And serendipitous weights just give excellent results, better than we know how, even for hard high-dimensional problems. This, of course, is connected with the fact that, well, we have a rigorous result, but the bounds are much too big. The constants are much too big. So that's how you could say a defect of the analysis. And so with that brings me to the end of what I wanted to tell you about. We think it's pretty exciting, actually. I hope you think so too. Thank you for attention.